I would like to thank my colleague Dejan Crnković, because he lent me some of the slides that I will present you today. So thank you, Dejan, for letting me. So I am now in the second part of our lectorium, which is entitled Construction of Non-Transitive Combinatorial Structures. So last time I was speaking about transitive combinatorial structures, and today I will speak about non-transitive combinatorial structures. And in the third part, in the last part, I will show you some applications of these structures that I was speaking in the first part and in the second part. And the applications will mostly be based on the codes. Okay, so here is the outline of my talk. So first of all, I will give you some basic definitions and preliminaries. Actually, I will just quickly remind you about basic things that we will need. Then in the second part, I will speak about tactical decomposition and orbit matrices, which is actually the method for constructing non-transitive combinatorial structures. And in this part, I will introduce you structures that are matrices, or structures that are matrices that are called orbit matrices. And why? Because in the third part, I will show you the method, which is based on the method that I introduced you last Tuesday, and the method that is used, that I will explain you in the second part. And this method will give us a non-transitive combinatorial structures that I would like to point you out today. Then in the example part, first of all, I will give you example of the ZA graph. This is just for illustration of the method. And then in the fifth part, I will show you how one can obtain very nice results by applying this method. In this last part, I will show you the nice results, but also here is the hidden part of finite geometry, in which I will show you how this method can also be used for obtaining very nice results that are connected with finite geometry. And in the last part, I will show you some open problems, and I will conclude my talk. Okay, so let us start. Again, an incident structure, just to remind you, is an order triple D, where P and B are non-empty disjoint sets, and E is an incidence relation. The elements of the set P will be called points, and the elements of the set B will be called blocks, and E will be called an incidence relation. In the last part of my talk, incidence, I will define partial geometry as an incidence structure, but their blocks will be lines. Then in a part where I will speak about graphs, points will be vertices, but this will be normal each time when this will be said each time when I will come to that part. Again, a very important mapping related with the incident structure is an automorphism. So we can define an isomorphism from one incident structure to another as a bijective mapping of points to points and blocks to blocks, which preserves the incidence. And an isomorphism from an incident structure D onto itself is called an automorphism of D. So we will here in this talk be interested in full automorphism group and automorphisms of the incident structure. The full automorphism group is the set of all automorphisms that is a group, and it is called a full automorphism group of D. When I will be related to the full automorphism group, I will said that this is a full automorphism group, but we can also have an automorphism group of incident structure, which are actually subgroups of the full automorphism group of the structure D. Okay, so in first part, we will need the designs. So T vk lambda design will be a finite incident structure D, satisfying the requirements that we have, that the size of the set P is V. Each or every element of the set B has exactly K elements of P, and every T elements of P are incident with exactly lambda elements of B. For T vk lambda design also, we know that every element of the point set is incident with exactly R elements of the set B. The number of blocks is denoted by B, and if B is equal to V, then the design is called symmetric. Okay, so the most famous design is Fano-plane or 2731 design, and when T is called when T is equal to 2, this design is called a block design. So here you have an illustration of Fano-plane or a 2731 design. It is a symmetric design having 7 points and 7 blocks. And for each design, we can relate to them an incidence matrix, which is a 0-1 matrix, having a 1 when 2 points are incident, and having 0 and having 0 otherwise. So here we are not labeling points, but you see that we have 7 points and 7 blocks. Okay, so this is very basic things, something that I was speaking about last time. Also a remark that when you have a T design, it is also an S design when S is larger than 1 and smaller and equal to T minus 1. Okay, so this leads us to a second part of the talk, in which I will introduce you tactical decomposition and orbit matrices. So a little bit about historical note. In 1958, Dembowski introduced the tactical decomposition in his paper. So he was probably the first one who started the study of tactical decomposition of designs. But this paper is about construction of projective planes. So this is something which is which definitely has ruins in finite geometry. In the paper from 1982, Becker, Mitchell, and Piper gave a lot of results that are concerning tactical decompositions of designs, and many of propositions that I will say today, and also will skip some proofs, can be found in this paper, and they are all regarding tactical decompositions of designs. Okay, so what is actually a tactical decomposition? So we are taking A to be incidence matrix of an incidence structure D. Okay, so we have an incidence matrix. What we are doing now, we are making a decomposition of the incidence matrix. So what is the decomposition? It is any partition B1 up to Bm of the rows of A and a partition of the columns of A. So if we take an incidence matrix, partition of the rows will in this talk be related to the blocks of D. So we are making partition of the blocks, and on the columns we are making a partition of the points. So now you can see actually that the incidence matrix of an incidence structure here is a B times V matrix. So rows are labeled by blocks and columns are labeled by points. Okay, so this is the decomposition. What we can do more? So if we are taking I to be less or equal to M and J less to equal to N, and if we are in the first step fixing a block from one class of the block partition, then we are interested in the number of points that is incident with this fixed block, and it is in particular class of the partition of the points. And of course, the block, fixed block, is arbitrarily chosen. Okay, in the similar way, we can count the number of blocks from the class of the block partition that are incident with arbitrarily chosen point from one class of the point partition. So if numbers alpha ij and beta ij are well defined in a way that they are independent from the choice of arbitrarily chosen blocks and points, then we will say that a decomposition is tactical. So if you can make a decomposition of a matrix for which these numbers are well defined, then you have a tactical decomposition of a matrix. And this can be defined for an incident structure D. Trivial tactical decompositions can be seen for one designs. So one trivial tactical decomposition is the composition for which M is equal to N and it is equal to 1. So what is it? It is actually the decomposition that is contained of just one class, just a second, so it is the decomposition that is contained of just one class of points and blocks. So what does it mean? It means that this is trivial tactical decomposition, and how we are sure that this is a tactical decomposition. But we have now, so that the number of blocks containing a point is constant. Why? Because we have one design, and for one design, this is a property, but also we have that the number of points contained in a block is constant. And this is also following from the property of one design. Okay, another trivial tactical decomposition is when we have that N is equal to V and M is equal to B. So actually this is the decomposition that is contained of, we can say, singletons, but it is contained of classes of size 1. And this is also one trivial tactical decomposition of one designs. Okay, so what is very important for us is the following proposition. But first of all, let us fix some labelings. So let D be an incident structure, and let G be the subgroup of the full automorphism group of the incident structure. We will denote the G orbits of points P1 up to Pn and G orbits of blocks by B1 up to Bm, and we will put that the size of each G orbit of points will be labeled with omega r, and the size of each block partition will be equal to capital omega I. Okay, R must go from 1 to n until the number of partition of points, and I must go from 1 to m up to number of partition of blocks. And we have the following proposition. The group action of G induces a tactical decomposition of D. And this is one very, very important property that will be crucial for the next slides that I will show you. So actually, if you have a group action, this will lead you to tactical decomposition. How we can prove that? So if we take 2 points from one class of partition of the points, which are different, and let B1 up to Bk be blocks that are incident with the point. Okay, and since x and y are in the same G orbit, okay, because they are in the same class of the partition of points, and we have a group action, so our partitions are G orbits. So they are in the same G orbit, so there exists an element from the group G such that the image of a point x is equal to y. Okay, then GB1 up to GBK are blocks from Bi, which is incident with y. The same idea will go in proving when you fix 2 blocks from the partition of blocks. Okay, so this is important to remember that when we have a group action of the group that is subgroup of the full automorphism group, then it induces a tactical decomposition. Okay, so let now D be a 2 vk lambda design. So we have a 2 vk lambda design, and we have that G is an automorphism group. Okay, so now let us denote by gamma ij the number of points from a partition of points that are incident with a representative of the block orbit Bi. Okay, so we are counting the number of points which are incident with a representative of the block from the block orbit. It is not difficult to prove these 2 conditions. First condition says that if you sum all numbers gamma ij, when j goes from 1 to the n, you will get a k. And the second one, which is giving us a condition that has also lambda inside. So remember that these 2 conditions are the ones that are connected with 2 vk lambda designs. Okay, so we can now define an orbit matrix for a 2 vk lambda design to be a m times n matrix M that has entries gamma ij, if this matrix is satisfying conditions 1 and 2. This matrix is called an orbit matrix for the 2 vk lambda designed and orbit length distributions omega 1 up to omega n and capital omega 1 up to capital omega m. It is the most easiest way to see it on an example. So if you take an incidence matrix for the symmetric 731 design or just symmetric 731 design. So this is an incidence matrix of this design. If we make a partition of points and blocks or partition of rows and columns, so you can see this partition. So we have 3 orbits on the points and 3 orbits on the blocks. And this is the partition of the points and the partition of the blocks. Okay, so how we will get an orbit matrix? An orbit matrix we will get if we are counting the number of points which are incident with representative of the block from the block orbit. So here take a look of this corresponding orbit matrix. So if we write the lengths of an orbit, this is 1, 3, 3 and 1, 3, 3. It means that we have 3 orbits on points and 3 orbits on blocks. One is of the size 1 and we have 2 of the sizes 3. The same goes on the blocks. Then 3 times 3 matrix is called an orbit matrix. So what number will be here? So what we are taking? We are taking the representative of the block from the first block partition. Since it is of size 1, we have only 1 block. And what we are counting? We are counting how many points are incident with this block from the partitions of the points. So we are counting. Here we don't have any. Then here we have 3 points from the second partition of the points. And here we don't have any point. The same is for this second row. So first of all, we are taking the representative, any representative of the block, second class of the block partition, for example, this block, and we are counting how many points are in this block. From the first partition, it is 1, from the second, it is 1, and from the third, it is 1. This block is arbitrarily chosen, so we can take first, second, or the third from this partition. The same goes from the last row of the orbit matrix. So we take any representative, for example, this 7th block. So from the first partition of points, there are no points together. From the second one, there is 1. And from the third partition, there are 2. So this is an example from for an orbit matrix obtained from this incidence matrix, and for, of course, for an acting of the group Z3. So cyclic group of order 3 is contained in the full automorphism group of the 731 design. We know that this group will make us a tactical decomposition. And if we build an orbit matrix by the rules that we said here, then we will have an orbit matrix for this design and for this cyclic group. Okay, so orbit matrices are used often in construction of designs with a presumed automorphism group. So one of the leaders in these methods of the construction of designs with presumed automorphism groups are Professor Janko. For example, in this paper, Janko and Trunvan Trung gave a construction of a new symmetric block design with the help of tactical decomposition. In this paper, Dan Senkovic also used the method for constructing designs with presumed automorphism group, and Stoichev and Tonchev in 2000 used the same approach in the paper Unital Designs in Planes of Order 16. So actually, this method of constructions are based on the following. So this method consists of two steps. The first step is construction of orbit matrices for the given automorphism group. So, okay, so what is the main idea that I should say before this first part? So in the result, we want to construct a design. So in these papers, this was always the idea. For the results, having a design, hopefully some new design. So how orbit matrices can be used in that way? You can presume an action of an automorphism group. And if you presume an action of an automorphism group, you can construct an orbit matrices for the given automorphism group. When you have all possible orbit matrices for the given automorphism group, then from these orbit matrices, you can try to construct a block designs for each of the obtained orbit matrix. And this second step is called indexing of an indexing. So it is actually a very, very computationally hard method in a way that from the given automorphism group and from the presumed action, you can obtain a huge number of orbit matrices. And from each of the orbit matrices, you can try to construct all possible block designs. This is not very easy thing to do, but in the result, you can obtain some new combinatorial structures precisely in this way designs. So these are just few papers that I pointed out and for which there are nice results which are proving the very nice functionality of the method. Okay. So this, of course, and what I must remark here, you have action of the presumed automorphism group. The orbit matrices are not trivial, so it means you have non-transitivity included. Okay. Let us go to strongly regular graphs. So we say that the graph is regular if all the vertices have the same degree. Graph will be strongly regular with parameters vk lambda mi if it has v vertices valency k, and if any two adjacent vertices are together adjacent to lambda vertices, while any two non-adjacent vertices are together adjacent to mu vertices. And strongly regular graph of type vk lambda mu is usually denoted by SRG vk lambda mu. Here there is an example of Petersen graph. It is a strongly regular graph having 10 vertices and with degree 3. It is very nice strongly regular graph that can be with a nice illustration. Okay, so the things that are related, one special partition that is related with strongly regular graphs is called an equitable partition. So let's see what is it. So a partition C1 up to Ct minus 1, which is a partition of the vertices of a graph G, is equitable. So this partition, we can say that it is equitable or regular if for every pair of indices ij, there is a non-negative integer bij, such that each vertex from a partition Ci has exactly bij neighbors of Cj, regardless of the choice of the vertex V. Okay, so if we can make this type of a partition of a graph, this partition will be called equitable partition. The matrix that will be T times T matrix with entries bij will be called a quotient matrix. And it is well defined if and only if the partition is partition of the vertices C0 up to C time minus 1 is equitable. I've written this reference to one book of Prager and Soicher, in which they were interested in low-ranked representations of graphs for sporadic groups. But this book is very nice reference for an equitable partition because they used quotient matrices in order to classify some of the distance regular graphs with particular ranks and obtained from sporadic groups. Okay, so what we can say about strongly regular graphs more. Let the gamma be a strongly regular graph with parameters vk, lambda, mu, and let A be its adjacency matrix. We can suppose that an automorphism group of strongly regular graph gamma partitions the set of vertices into T orbits, of which are each of the size ni, where I goes from 1 to T. This partition is equitable. And the quotient matrix, it can be easily seen that the quotient matrix R that has elements Rij satisfy the following conditions. So labeled with 3 and 4, these two conditions will help us to define an orbit matrix for a strongly regular graph. So T times T matrix R with entries satisfying these two conditions is called an orbit matrix for a strongly regular graph with parameters vk, lambda, mu and orbit length distribution n1 up to nt. Analogously, with orbit matrices of a block design, here we can speak about orbit matrices of a strongly regular graph. Tactical decompositions of designs is here an equitable partition. So quotient matrices and orbit matrices are of strongly regular graphs are actually analog to orbit matrices of two designs, but here we are interested in graph. In the same way as orbit matrices of two designs were used for a construction of designs, here orbit matrices or quotient matrices, if you want to say in that way, of strongly regular graphs are used for a construction of strongly regular graphs in the papers. So Bekbahani and Lam introduce this method for constructing strongly regular graphs, but they use the construction method for obtaining strongly regular graphs with non-trivial automorphism groups. And that was in 2011. A little bit later, Trnković and Maksimović in their paper gave a generalization of the method in which they were able to make a method for construction of strongly regular graphs having an automorphism group of composite order. So it does not have to have restrictions on an automorphism group. Okay, so let us just remind quickly to a D-class association scheme that we introduced last time. A D-class association scheme on a finite non-empty set omega is an ordered pair of this non-empty set omega and a set of relation R, which is called the set of non-empty relations on omega, such that the following axioms hold. R is the partition of omega x omega. R0 is the identity relation that is element from the partition R. And for every relation R, Ri from R, its converse is also is equal to Ri, and there are constants Pij,k that are known as the intersection numbers of the association scheme. These intersection numbers satisfy the following condition, which says that for every pair xy from the set of the relation R chi, the number of elements for which z is from Ri and zj is from Rj equals Pij,k. They were introduced by Bose and Shimamoto in 1952. And if you take A to be the adjacency matrix that is corresponding to each of the non-empty relation Ri, it is a 0-1 metric defined that 1 is on the position if 2 elements are in the relation and 0 otherwise. Each of the matrices that are corresponding to the adjacency matrix of particular relation represents a simple graph gamma I on the set of vertices. And actually we can say that the graphs gamma I form an edge coloring of the complete graph. And we can say that we can define an equitable or regular partition of an association scheme with D classes to be a partition of X, which is equitable with respect to each of the corresponding graphs gamma I when I goes from 1 to up to D. Okay, so this is something that was that I wanted to explain you very in details because it is related with the method that we used. Okay, these 2 slides are the slides that I copied from the last talk. Because in the last talk, I was speaking about transitive action. Just to remind you, we can say that the group is acting transitively if it has only one orbit. And one example of transitive action is action of symmetric group on the set of n elements. Why we needed a transitive action? We needed a transitive action because we were speaking about the method from which you can construct structures on which their full automorphism group acts transitively. In other words, you can classify transitive structures from some particular finite groups. Okay. In a relation, especially here in this theorem, we were speaking about construction of transitive one designs. We also remarked that this method can be used for constructing transitive graphs. So just to remind you, if you have that the group G acts transitively on the set omega, and if you fix one element from omega, and if you have that delta is an orbit of stabilizer G alpha, then delta prime defined in this way will be also an orbit of the stabilizer. And this orbit will be called an orbit of stabilizer paired with delta. Okay, when these two orbits, delta prime and delta, are equal, then this orbit is said to be self-paired. Why we need this? We need this because in the previous method, when you have that two sets are equal, and you for your base block you have that delta is a union of self-paired and mutually paired orbits of stabilizer G alpha, then design will be symmetric, self-dual design, which is fantastic because when you have symmetric design, it has symmetric incidence matrix. Self-dual design, you have zeros on the diagonal, but what does it mean? It means that this incidence matrix of the design is actually adjacency matrix of a regular graph with regularity equal the size of the based block. Excellent. So how we can construct non-transitive combinatorial structures using these approaches that I was saying, that I was explaining you so far. So the best way how I can explain you is on one very nice example that I'm using here just to illustrate you the method. So actually combining incidence matrices of transitive one designs, one can construct adjacency matrix of a non-transitive graph. So to remind you, last time I told you that when you are using particular finite group that is acting transitively, you can classify graphs. If you're interested in strongly regular graphs, you can do also. But this graph has the property that it is transitive. So how we can obtain that? How we can obtain non-transitive ones? So let us start from the group U43 that is extended with Z4. This is the full automorphism group of a strongly regular graph on 101 to 6 points. This strongly regular graph is known as Zara graph. Okay, and this group acts on the strongly regular graph with these parameters. So the action is transitive. Okay, so we know that this group, one of the subgroup that it is contained in this group is unitary simple group U42. This group acts on, since it is a subgroup of the full automorphism group of strongly regular graph, it acts on that graph, Zara graph, and it is acting non-transitively. So it is acting in 3 orbits, and the orbits are of sizes 1, 45, and 80. It is easily to obtain the orbit matrix. This is something that we can calculate, and what we can get is an orbit matrix that has these entries. Okay, so what actually we know that this subgroup is acting on the Zara graph in this orbit matrix. But what can we also hope to get? We can hope to take this fixed orbit matrix with this subgroup U42, and we can hope that there are some other graphs with that are preserving the action of the group U42 with this orbit matrix, but that are not isomorphic to the one that we started. This graph will always have this group acting with this orbit matrix, but maybe the graph that we will get will not be the isomorphic with the starting graph. Okay, so in this example that I'm showing you with this orbit matrix, it is an easy example because when you try to find all possible graphs with this orbit matrix, you get two graphs. One is the graph that is isomorphic with a starting graph, and another graph is called a strictly Desa graph. It is a graph which is with the parameters that are written in a similar way as for strongly regular graphs, but it is not a strongly regular graph, it is a strictly Desa graph, and the full automorphism group is of this type. Okay, so what I wanted one more thing to say is the fact that in going from the orbit matrix with this subgroup and obtaining a new graph from this orbit matrix, we were using actually the method that is transitivity, that gives you transitive results in a way that for each of the element of an orbit matrix, we needed to calculate all the possible matrices that can be put in here. So actually, we are gluing this orbit matrix for obtaining the adjacency matrix of a graph. Just to remind you, the Zara graphs are very nice generalization of strongly regular graphs. They were introduced in 1999. And they are defined to be a Desa graph with parameters VKB-A is a K-regular graph having V vertices in which any two vertices have A or B common neighbors. So we are calculating just the neighbors of the vertices, and it is always the fact that they have A or B common neighbors. This is the definition of the Desa graph, but it can be also we can also say strictly the Desa graph if this Desa graph has diameter 2, but it is not strongly regular. So that's why I mentioned that this graph is strictly the Desa graph. It has parameters of the strongly regular, but it is not strongly regular. Okay, so this was just an example for try to illustrate you the method. But now I will show you how we implemented this method in obtaining very nice results in which we obtain some new strongly regular graphs, but moreover, one result that is related with finite geometry. Okay, so we in this paper we published one result in which we show construction of strongly regular graphs with these parameters, and we constructed some new strongly regular graphs that have these parameters. Before this work, it was known that up to isomorphism, there have been known two strongly regular graphs with these parameters. One, which is known as van Linde-Schreiber graph, and having the full automorphism group of order 116640, and the second graph having full automorphism group of order 5832. So what we've done in this paper, actually, our starting graphs were these two known graphs, and from these two known graphs, presuming an action of a subgroups of full automorphism groups of these two graphs, we constructed some new strongly regular graphs. In total, we constructed 12 new strongly regular graphs, and here is the table. Here is the table of it. So we were able to prove that, and the method that we used is based on orbit matrices. We showed that there are exactly 3 non-isomorphic which are invariant under a subgroup of order 360 of the automorphism group of gamma 1, which is the full automorphism group of the first known graph, and exactly 11 of those that are invariant under the group of order 972. Here are the full automorphism group of those structures, but those 3 ones are actually here, gamma 14, gamma 13, and gamma 1, while the other one that are invariant under 972 are the rest. I will just quickly go through the method, mostly through the results to show you how we done that. But I will focus on this second known graph and the second automorphism group. I will later tell you why. So we started from the group of order 5832, which is the full automorphism group of the second graph that was known before. And we've taken the subgroups of order 972. There are exactly 5 conjugacy classes of those subgroups, for which 2 are acting transitively on 81 vertices, and from these two subgroups we obtained known strongly regular graphs. The third subgroup of order 972 was acting on the set of vertices of the graph gamma 2 in 3 orbits and with this orbit matrix. Using this orbit matrix and the method that I was explaining you, we constructed a new strongly regular graph with the same parameters, having the automorphism group of order 1944. 2 subgroups, H4 and H5, of size 972, produced the same orbit matrix. And from this orbit matrix and from these 2 subgroups, we obtained the 4 non-isomorphic strongly regular graphs. Gamma 2, which is the graph from which we started, gamma 4, gamma 5, and gamma 6, 2 of them having the full automorphism group of order 972 and 1944, while for H5 we obtained 12 non-isomorphic strongly regular graphs, and one of them having the full automorphism group 3888. Okay, so we can just again take a look on the table, and on this table you have a labeling of the graph and the size of the full automorphism group. and it is always the strongly regular graph having these parameters. Okay, so in this table, you also have a last column, which is called maximal click of maximal click size of the set gamma. Okay, so this will be very, very important for this last part of my talk for today. So first of all, I will just give you a few basic definitions. So partial geometry. So today we were speaking about two types of incident structures, designs and graphs. And now we will speak about partial geometry. So a partial geometry having parameters S, T, and alpha, or shortly written PG, ST, alpha, is a pair of a set P called points and the set L called a set of lines with an incidence relation between points and lines satisfying the following axioms. First of all, a pair of distinct points is not incident with more than one line. Every line is incident with exactly S+1 points, and every point is incident with exactly T+1 lines. And the last axiom says for every point P, which is not incident with a line L, there are exactly alpha lines which are incident with a point P and also incident with some point incident with L. And this is a definition of a partial geometry. In this very nice paper, Strongly Regular Graphs, Partial Geometries, and Partially Balanced Design, written by Bose, there are many nice results about partial geometries. So, in terms of the parameters ST alpha, we can calculate the number of points and the number of lines of a partial geometry. And it is easily calculated. You have formula for obtaining how many points and how many lines you have. The structure that is related to partial geometry is one structure which is called a dual of a structure. So if you have a partial geometry, then the incident structure, which can be defined having as points the lines of our particular partial geometry and having as lines the points of our partial geometry, where a point and line are incident if and only if the corresponding line and the point of G are incident, is called a partial geometry with parameters T S alpha, and it is a dual of our geometry. So actually, dual of partial geometry is defined to be a dual incident structure of our partial geometry. Why I am now introducing this very nice geometrical structure? They have a nice property. If you have a partial geometry with point set P and lines set L, and if you build a point graph, which will be the graph with vertex set P, where two vertices are adjacent if the corresponding points are collinear, you will have the result of both, that point graph of a partial geometry is a strongly regular graph. Not just point graph. You can take a look also on the graph having as vertices the lines of partial geometry, where two lines are adjacent if they share a point. This graph will be called a line graph, and this graph is also a strongly regular graph. The parameters of these strongly regular graphs that are line graphs and point graphs of a partial geometry can be calculated with this formula numbered with 6. So you can, if you know PG with parameters ST alpha, you can calculate what could be the parameters of a strongly regular graph. Examples of partial geometry. So if you have PG ST alpha with alpha equal to S plus 1, it will be a Steiner 2V S plus 1 design. So it is a Steiner 2 design. Or dually, if you have that alpha is T plus 1, the dual geometry will be a Steiner design, but now it will not have V points, it will have B points. And each block will be equal to T plus 1. If alpha is equal to S and alpha is equal to T, then G will be a net of order S plus 1 and degree T plus 1. And the partial geometry having alpha equal to 1 is a generalized quadrangle. And we can say that a partial geometry is proper if alpha is bigger than 1 and smaller than minimum of S or T. And this will be important. So what is very important to understand? So when you have a strongly regular graph whose parameters nk lambda mu or vk lambda mu, whatever you wish, can be written in a form of equation 6 for some integers st alpha, then this strongly regular graph will be a pseudo-geometric graph. It means that its parameters satisfy conditions of the parameters of a graph to be a point graph or a line graph of a partial geometry. But it does not necessarily mean that this graph will be a point graph or a line graph of our partial geometry. It will be called a geometric one if there really exists a partial geometry with parameters is st and alpha, such that gamma is the point graph of G. So you can have a lot of strongly regular graphs whose parameters satisfy these conditions, but it does not mean that inside of these strongly regular graphs, you can construct this nice finite geometry structure. Bose in 1963 gave a very nice condition, which is very helpful in showing whether some pseudo-geometric graphs are geometric also. So a pseudo-geometric strongly regular graph with parameters satisfying condition 6, so which can be calculated in this way, is geometric if and only if there exists a set of B clicks of size S plus 1, such that every 2 clicks from S share at most one vertex. And this condition is very important for checking whether your pseudo-geometric graph is geometric. Okay, so known proper partial geometries can be divided into 8 types. 4 of them are obtained from infinite families, and 4 of them are obtained from sporadic geometries and that are not belonging to any known infinite family. More about these families and some details you can find in the chapter of handbook. But why I'm mentioning this here? I'm mentioning this here because One of these four examples, these sporadic examples, is a partial geometry with parameters PG552 that is discovered by Van Lint and Schreiber in 1981, and it is explained in this paper. If you calculate the parameters of the point graph of this partial geometry, you will obtain that the parameters of the graph is 81, 30, 9, and 12. This graph is related with one Lint-Schreiber geometry is invariant under the elementary abelian group of order 81, which is acting regularly on the set of vertices. So the only known, previously known partial geometry is this one, constructed by Van Lint and Schreiber. This partial geometry has the full automorphism group of order 58320, and the corresponding strongly regular graph is gamma 1, which is the gamma 1 from the first table that I showed you, which has the full automorphism group of this size. So, in the work that I was explaining you non-transitivity action and how we obtain some new strongly regular, non-isomorphic strongly regular graphs, I showed you that we obtained 12 new strongly regular graphs with these parameters. So all these 12 new strongly regular graphs with these parameters are pseudo-geometric. It means that they are satisfying conditions. But what we were able to do and what we obtain is one very, very nice result, which says that one of these new strongly regular graph is actually geometric. And this graph from this one, this geometric one, we obtained a new partial geometry, PG with parameters PG552, that is not isomorphic to the partial geometry that was known before. We did not prove the existence because the existence was already proven, but what we were able to do, we were able to construct another partial geometry with the same parameters, which is not isomorphic to the one constructed by Van Lint and Schreiber. And in this in this check for obtaining whether the graph is geometric or not, we were using the condition of Bose and the number of maximal click size. So we shown that for the graph gamma 12, it is the one that I pointed out here. This graph has 108 6 clicks. And these 6 clicks are those S+1 sets that we need for PG. And 81 of these 6 clicks form the lines of the new partial geometry. The full automorphism group of this partial geometry is of the order 972. This group acts non-transitively. It acts in 2 orbits of size 27 and 58. And this new is self-dual. It means that point graphs and line graphs are mutually isomorphic. I have to note here that the isomorphic partial geometry, PG552, was simultaneously and independently by our constructed by Vedran Kachadinac, but he used another method which is totally different, and it is based on some geometrical structures. So by now, as far as I know, up to my knowledge, there are 2 PGs that are mutually non-isomorphic and having these parameters. This leads us to the last slide of my talk, in which I just want to conclude that I tried to explain you the method that we use and try to show you how one can use these very nice properties of structures being transitive or non-transitive to obtain nice new results. The open problems here are, you have a bunch of open problems. When you lose transitivity, it is again very hard to do some type of classifications, but it is always an open problem to try to make a classification of non-transitive to designs or distance regular graphs or strongly regular graphs that are invariant under some particular group or having some particular orbit matrix. As I shown you, we were able to use this method to prove and to construct some new structures, but it can also be a method for proving existence of related combinatorial structures, and in this way for obtaining some very nice geometrical structures. For proving existence, it is always one of the open problems is the list of Brouwer, in which you have the parameters of strongly regular graphs. And with this slide, I would like to thank you all for attending this talk. In the next Tuesday, I will focus on applications, and I will try to show you how one can use these things that I was speaking about to obtain, to make some applications, especially in coding theory. Thank you very much for your attention.
Okay, Andrea, thank you very much for your talk. And sorry, I couldn't participate your talk at the beginning. And actually, I'm sorry because of this schedule. Actually, we have lost many participants because the Congress just started yesterday. So, for example, Gareth John, he wrote me and he asked to sorry, and he will try to watch video lecture by you, so that is the benefit of our online lectures. So thank you very much. And actually, are there any questions to Andrea due to her talk? Well, at the beginning of your talk, you presented one more partial geometry with parameters 552, right? Yeah. But what do you think? Are there any other non-isomorphic partial geometry could be found?
Yes, well, there are probably many methods in which you can try to find some other non-isomorphic partial geometries. In our work also, because we were going from graphs to partial geometries. I don't know, some people are probably trying to go directly to partial geometries, but even in our approach, there are still places where we can search, because we are limited with computational methods. And if we could make some bigger progress in order to obtain more strongly regular graphs with these parameters, they are actually potentially point graphs of this partial geometry that does not have to be isomorphic to the one that we obtained so far.
I see.
So yeah, it is still an open question, because as far as I know, there are for now just two non-isomorphic ones.
Well, but it is unknown how many partial geometries are there with these parameters.
Yeah, two. Our and the one that is that was constructed before of one lint. Yeah.
Yeah, I see.
Yeah, of course, the same method can be applied for another strongly regular graph, taking care of some other partial geometry. We are trying to do that. Yeah. So
Yeah.
far, we still didn't get any, but it's not easy work. We are trying
sure,
to.
of course it is not so easy, yeah.
It
So
is.
good luck in searching, yeah.
Thank you.
Well, and I have one more, maybe stupid questions. So you explain us that there are some connections between strong irregular graphs and partial geometry. And you also mentioned about strictly these-are graphs, right? Yeah, which is, well, these-are graphs are generalization of strong irregular graph. So what do you think? Is it possible to find some relationships between these-are graphs or strictly these-are graphs and partial geometries?
Well,
or something like partial geometry.
I don't know.
Yeah, me too.
I don't know. It is interesting question. I don't know, because it can probably be related, because since the graphs are generalization of strongly regular graphs, then maybe there are some structures that can be generalized and connected with these graphs. But in this moment, I don't know. I don't know.
Yeah.
Yeah.
It would be interesting.
It would be interesting, yeah, because these graphs are, they are nice structures.
Right, yeah. We know something about combinatorial structure and graph theoretical structure of this family of graphs, but we nothing know about what about geometry, yeah. So it would be interesting to understand,
Yeah. This is a very nice question for finite geometries also, yeah.
Okay, thank you, Andrea. Are there any other questions to Andrea? Or maybe some comments? Well, if not, then let us thank Andrea again for her very nice, interesting talk. And the next talk will be in 1 week, so next Tuesday, the same time. And yeah, I hope that a little bit more participants will join us for the next time. Okay, see you in 1 week.
Thank you very much,
Andrea. Thank you, yeah.
See you.
Yeah, and yeah. Leo, thank you very much. Yeah, it was really very nice talk. Yeah.
Thank you, Leo.
Yeah. See you in 1 week. Yeah. Okay, Joseph. Hi. Yeah.
Hi. Thank you. Thank you.
See you next time. Yeah. Okay.
Yes.
Thank you. Thank you for joining us. Yeah.